In this next section, we are going to explore how to find the nth roots of a complex number. Now, if you recall in our last section, I mentioned that the powerful thing about De Moivre's theorem is that it not only applies to integer powers, but it also applies to powers such as half, and therefore we can use it to find the roots of a complex number. What do I mean by roots? And what are some concepts that I need to have about roots before I start? Well, let me answer your question. First of all, let us consider the following question. How many roots do you think I would expect an equation that looks like this to have? Well, it is a usual quadratic equation, even though the variable I use is z. In this case, I expect it to have two real roots. In fact, I know the roots will be 2 and -2. Then what if I have a following equation instead? And now this is cubic, so how many roots do you think this equation is going to have? Certainly, I would expect this equation to have 3 roots. The previous one was 2 roots. And this is from what we have learned. In fact, there is a theorem which is called the fundamental theorem of algebra, which says that any polynomial of degree n will have n roots. In this case, this is a cubic polynomial, so I expect it to have 3 roots. But I know because there are complex numbers here, or rather there is an imaginary component, I would expect there to be complex roots, which is to say my roots need not be real. Finally, just to hammer in the point for one last time, how many roots would this equation have? Well, it is to the power of 8, so I expect this equation to have 8 roots. And because there are imaginary terms involved, I would expect their roots to be complex. So for the first one, we had 2 real roots. Now in general, mathematicians used to wonder, is there any pattern to the way the roots are distributed? Perhaps there is something that can be observed. So let's take a look at this applet over here. Now suppose I have this complex number z and I can move it anywhere along the Argand plane. And I want to see the position of its roots. So suppose z is over here, okay, which is 1.84 minus 0.94i. Then the 3 cube roots of z would be these 3 points. And we notice they form a very nice triangle around the origin. Right, and they are all equally spaced from one another. In fact, I see they form sort of like an equilateral triangle. What if I move z? Does the relationship between the 3 roots change? No, instead I observe, regardless of how I move z, the 3 roots will always be equally spaced, and there will always be 3. They will be equal distance from one another with the same angle between them, and they are all the same distance from the origin. But does this only apply for 3 roots? Is it a special case? Let's add on a few roots. Now if I have 4 roots, would it be any different? Well, no. And even if my number was a real number, it is still entirely possible. See, it can be a purely imaginary number or a purely real number, and the 4 roots will still behave in the same way. Wow, this is quite amazing. What if I have 5 roots? Then what I get is a pentagon centered at the origin. And not just any pentagon, but a regular pentagon with all the vertices equally spaced. So I see, no matter how many roots I add, I can keep adding roots. They will all be equally spaced about the origin, regardless of where my z is. And this is the concept we are going to use. Okay, we can then determine the main difference between each root, which is that the distance from the origin is the same, but the angle is different. Okay, and hence what I know about the roots of a complex number is this. They will all have different angles, such that all the roots are distributed equally about the origin, but the modulus of all these should be the same. We are going to look at how we can find out the values of these roots now. I will begin by explaining the steps we could take to find the nth roots of a complex number w, such that z to the power of n equals to w, and then I will also attempt to explain the rationale for each step along the way. So first of all, if we could write Zn equals to W, we say that Z is an nth root of W. For example, 2 squared equals to 4. Right, so 2 is the square root of 4. But what we are doing here is simply extending this to the realm of complex numbers. So the first thing we're going to do, because we are employing De Moivre's theorem really largely deals with angle as well as modulus. And hence, it is not going to be very useful if our complex number is in Cartesian form. So suppose it is not already in exponential or polar form, then I'm going to express it in exponential or in polar form. And it doesn't matter which one I begin with. So it depends on the question. If the question were to ask me to express the roots in exponential form, for example, I might therefore choose to begin by expressing W in exponential form. Now the next thing we can do is to express W in n-1 equivalent ways by adding 2k pi to the argument. So what we are saying is this is the eigenplane. So suppose W was a point somewhere here, then I know that the argument of W is theta, and the modulus would simply be this length. But suppose I formed a new complex number by adding 2 pi to the argument of W, then what would happen? Then my new argument will be theta plus 2 pi, and we notice that I will arrive back at the same complex number. What if I add 4 pi? Again, I will go one more complete round, and yet I end back at the same complex number. So by adding 2k pi, I am expressing W in n equivalent ways. Okay, because they are all the same complex number, and what I am doing is just generating n-1 different copies of W. Okay, so depending on the value of k, I could have one with the argument of theta, or one with the argument of theta plus 2 pi, so on and so forth. But as we can see from an Argand diagram, these are all essentially the same complex number. So whether it is in polar form or exponential form, the same will apply. The modulus would remain the same, but the argument would simply be replaced by theta plus 2k pi. Okay, and I'm not effectively changing W because this is still true. I still get the same point on the Argand plane. Now why do I want to do this? Because later on, in the next step, I'm going to state the nth roots of W using De Moivre's theorem. So by De Moivre's theorem, I know that the modulus of Z would be the modulus of W to the power of 1 over n, which is R to the power of 1 over n. And what about the argument of Z? I know that the argument of Z would be the argument of W divided by n, which is how I arrive at theta plus 2k pi over n. We find that because of this k over here, if we allow k to take on values such as 0, 1, 2, 3, I would therefore get the different roots. And because I have now divided by n, all these roots will be equally spaced from one another. They will have the same angle from each other. Yeah, I will demonstrate later on using an example exactly what I mean. And these will all be the roots of Z. So what are some suitable values of k? I know that in all, I should have n roots. Okay, so I could start with k equals to 0 and then go 1, 2 and so on up till n minus 1 for a total of n roots. Or I could also start from 0 and then add 1 and subtract 1. Okay, so up to this point I have 3 roots, plus minus 2, 5 roots, so on and so forth. So the main thing we have to remember is that in the end, the argument of each root over here must fall within the principal range of negative pi to pi. Okay, so you would find, what if I hadn't done step 2 earlier on? Then I will only end up with one root, which is theta, with an argument of theta over n. And I will not be able to generate all the other subsequent roots. Because of what we have done with the values of k, you will find that I am actually able to generate all the roots. Now sometimes after generating the roots, we find that the values are not within a principal range. So what we would then do is to subtract off 2 pi or add 2 pi until it falls within the range. We will now look at an example to illustrate this concept.